Why waste a vast cosmos on us alone? Carl Sagan. At Los Alamos National Laboratory in New Mexico, an unusual conversation occurred during a lunch break. Among the scientists present was Edward Teller, known as the father of the hydrogen bomb. They began discussing the possibility of extraterrestrial life, speculating about aliens visiting Earth in flying saucers. It was a lighthearted conversation among colleagues who were largely skeptical of such notions. In the midst of the discussion, Enrico Fermi, a renowned physicist and Nobel laureate, posed a simple question. Where is everybody? The starry sky appears vast to us, but we actually observe only a tiny fraction of our cosmic neighborhood. On the clearest nights, we can see up to 2,500 stars, almost all of which are within 1,000 light years, a mere 1% of the Milky Way's diameter. There are between 10 sextillion and 1 septillion stars in the observable universe. To put it simply, for every grain of sand on all of Earth's beaches, there are approximately 10,000 stars in space. Between 5% and 20% of these stars are similar to our Sun. Even using the most conservative estimates, that amounts to 500 quintillion Sun-like stars. Now imagine that 1 in 5 of those stars hosts a planet like Earth, a planet that could have liquid water and conditions suitable for life. That would be 100 quintillion Earth-like planets. This means that for every grain of sand on Earth, there are about 100 potentially habitable planets. Think about that the next time you find yourself on a beach. Consider that over billions of years, even if just 1% of these planets develop life, and on 1% of those planets, life evolves to an intelligent level similar to ours, we would have 10 quadrillion intelligent civilizations in the universe. In our Milky Way galaxy alone, this could translate to 1 billion Earth-like planets and 100,000 intelligent civilizations. For years, SETI, Search for Extraterrestrial Intelligence scientists, have been trying to detect signals from alien civilizations. If there are indeed over 100,000 intelligent civilizations in our galaxy, and even if a fraction of them are transmitting radio signals, or at least laser beams into space, shouldn't we have detected something by now? Yet, we haven't heard a single sound. Nothing at all. This raises the profound question: where is everyone? Our sun is relatively young on the cosmic timescale. Everywhere in the universe, there are much older stars with Earth-like planets orbiting them. It's logical to assume that civilizations on these planets could be far more advanced than ours. Let's compare Earth, which is about 4.5 billion years old, to a hypothetical planet X that is 8 billion years old, the average age of planets orbiting red dwarfs, the most common stars in the universe. If life on planet X evolved similarly to life on Earth, imagine the technological advancements they could have achieved with an additional 3.5 billion years. A civilization just 1,000 years ahead of us might possess technology that seems like magic to us. A civilization 1 million years more advanced could be as incomprehensible to us as our modern society to a chimpanzee. And that's only considering a 1 million year difference. You might have heard of the Kardashev scale, a famous method of categorizing intelligent civilizations based on the amount of energy they harness. A Type 1 civilization can utilize all the energy resources of its home planet. We humans are approaching this level. A Type 2 civilization can exploit all the energy of its star, although it's challenging to envision how this would be accomplished. A Type 3 civilization can harness energy on the scale of its entire galaxy. The concept is almost beyond our imagination, isn't it? Consider Planet X with its additional 3.5 billion years of development. If its civilization were similar to ours and had advanced to become a Type 3 civilization, they would likely have already mastered interstellar travel and colonized the entire galaxy. One theory explaining how much colonization could occur was proposed by astrophysicist Michael Hart. Imagine self-replicating machines that travel to other planets, utilize local resources to reproduce, and then send their copies onward. These are known as von Neumann probes, named after the famous mathematician. Even without faster-than-light travel, it would take less than 4 million years to colonize the entire galaxy, a blink of an eye on the cosmic scale. If you're still skeptical, consider this. A team of astronomers from the University of Rochester created a computer simulation illustrating how colonizing the Milky Way could unfold. In their model, the ships travel very slowly, only 10 kilometers per second, with a maximum range of about 10 light years. It takes them 300,000 years to reach their destinations. Each colonized system can send out a new ship every 100,000 years. They have plenty of time. This interval exceeds the entire history of human civilization. As the simulation shows, even with these modest parameters, an advanced civilization could populate most of the Milky Way in approximately 1 billion years. Assuming that even 1% of intelligent civilizations can progress to become Type 3 civilizations, there should be at least 1,000 such civilizations in our galaxy. We would surely detect their presence, wouldn't we? Yet, that's not happening. Could it be that we misunderstand something about the universe? Or that advanced civilizations are deliberately hiding from us? Or maybe we are truly alone in the Milky Way, or simply appeared early? To explore the basic explanations of the Fermi paradox, let's consider insights from Max Tegmark, Jim Al-Khalili, Nick Bostrom, and an article by Tim Urban. Unfortunately, if you ask 10 different scientists where is everyone, you'll likely receive 10 different answers. It's reminiscent of when people debated whether Earth was round or believed diseases were caused by evil spirits. Humanity has come a long way since then, and our ancestors may seem trivial and unenlightened to us. However, when it comes to the question of extraterrestrial life, we are still at a similar level of understanding. There are two main categories of explanations for the Fermi paradox. The first suggests that we see no traces of Type 2 or Type 3 civilizations because they do not exist. The second proposes that such civilizations do exist, but we do not observe them for various reasons. Proponents of the first category point to the problem of non-exclusivity. Using mathematical calculations, they estimate that if there are thousands or millions of highly advanced civilizations in our galaxy, at least one of them would have contacted us by now. If an advanced civilization could travel between stars at only 10% the speed of light, which is quite realistic, it could colonize our galaxy in about 1 million years. That's a relatively short time on a cosmic scale. For example, the fastest space probe launched from Earth has reached about 0.07% of the speed of light. At that speed, we could colonize the galaxy in 150 million years. Think about it, 150 million years, and the Milky Way has existed for billions of years. So perhaps there is no one out there, or something else is happening throughout the universe. This something else is known as the Great Filter. Throughout the ages, from pre-biological conditions to the emergence of advanced intelligence, there are barriers that thwart nearly all attempts at life. Somewhere within this long evolutionary process lies a particularly formidable barrier, one that is extremely unlikely or even impossible to overcome. This concept of the Great Filter was proposed by economist Robin Hanson. The pressing question is, where exactly does this filter occur on the timeline? Depending on where the Great Filter lies, humanity may be in one of the three possible realities. We are rare, we are first, or we are in deep trouble. Our only hope is that the Great Filter is behind us, that we have already overcome it. This would imply that it is exceedingly rare for life to reach our level of intelligence, which would explain the absence of Type 3 civilizations. However, it would also mean that we are among the few exceptions, having progressed this far. At first glance, this notion seems akin to the ideas from 500 years ago, when people believed Earth was the center of the universe. It appears presumptuously self-important. It suggests that we are special. However, scientists seriously discuss the observer selection effect. Anyone contemplating their own rarity is inevitably part of the success story of intelligent life. For example, you are an exceptionally rare organism because all of your ancestors successfully passed on their genes, leading to countless descendants. Assuming we are indeed special, when did we become so? What is the stage we have surpassed that hinders everyone else? One possibility is the very origin of life itself. It took about 700 million years for life to emerge on Earth. Despite extensive efforts, we have been unable to replicate this event in laboratories. If this is truly the Great Filter, then not only is there no intelligent life anywhere else in the cosmos, but there may be no other life at all. Another possibility is that the Great Filter occurred during the transition from simple prokaryotic cells to complex eukaryotic cells. Prokaryotic cells are small and simple. They lack a nucleus, and their DNA floats freely within the cell. They have a few internal structures and include bacteria and archaea. In contrast, eukaryotic cells are larger and more complex, containing a nucleus where DNA is stored, and various organelles, each performing specific functions. For instance, mitochondria function as tiny power plants within the cell. Eukaryotic cells containing such organelles are found in plants, animals, fungi, and some unicellular organisms. The transition from prokaryotes to eukaryotes represents a significant leap in complexity and capability. After prokaryotes emerged, they remained relatively unchanged for nearly 2 billion years before making the next evolutionary leap, developing a nucleus. Many scientists believe this event may have occurred only once in Earth's history. If this is the Great Filter, then the universe might be filled with simple prokaryotic cells and nothing more. There are other possibilities as well. For instance, some consider the emergence of artificial general intelligence as a candidate for the Great Filter. Although the leap from less intelligent life to intelligent life might not seem miraculous at first glance, cognitive scientist Steven Pinker rejects the notion of inevitable upward progression in evolution. Since evolution does not have a predetermined goal, it simply works through adaptations that are most beneficial for a given ecological niche. The fact that technological intelligence has only emerged once on Earth so far suggests that this outcome of natural selection is rare, and by no means an inevitable step in the evolution of life. Any possible Great Filter must involve something as rare as a 1 in a billion chance. One or more completely random events would have to occur to create an extraordinary exception. Therefore, something like the transformation from single-cell to multicellular life is unlikely to be the Great Filter. Scientists have found that this transformation happened independently at least 46 times on Earth. It occurred in plants, animals, fungi, and algae. Each time, it was a separate, independent evolutionary process. This suggests that it is clearly not a super rare exception. Similarly, if we were to find a fossilized eukaryotic cell on Mars of local, non-terrestrial origin, it would rule out the leap from simple to complex cells as a possible Great Filter. It would also rule out everything that occurred prior to that in the evolutionary chain. After all, if such a transition happened on both Earth and Mars, it could not be considered a 1 in a billion chance. If we are truly rare, it may not be due to a random biological event, but because of the unique characteristics of our planet. While many planets may be similar to Earth, the specific conditions here, such as the peculiarities of our solar system, the presence of a large moon, or other factors about Earth itself, may be exceptionally favorable for life. This is known as the unique Earth hypothesis. Another hopeful scenario for humanity is that the conditions of the universe have only recently, for the first time since the Big Bang, become conducive to the evolution of intelligent life. In that case, we, along with many other species, may be on the path to superintelligence, and it just hasn't happened yet. We may be here at the right time to become one of the first civilizations capable of colonizing space. Here's the evidence. Consider the prevalence of gamma-ray bursts, which are massive explosions observed in distant galaxies. Earth, in its early days, was a very turbulent place, with frequent asteroid impacts and volcanic eruptions. This lasted for several 100 million years. It was only after these cataclysmic events became less frequent that life was able to thrive on Earth. A similar scenario could have played out in the early universe, where cosmic cataclysms prevented life from evolving beyond a certain point. Now, as astrophysicists have noted, we may be in the midst of an astrobiological phase transition. This could be the first time in cosmic history that life has been able to evolve for such a long period without being interrupted by large-scale cosmic events. And now for more bad news. If we are neither rare nor early, then the Great Filter must lie somewhere in our future. This suggests that life regularly evolves to our level. but something invariably prevents it from progressing any further. We are likely not an exception. One possible future filter could be natural disasters, such as gamma-ray bursts, that occur regularly and wipe out life. Another candidate is the possibility that nearly all intelligent civilizations destroy themselves once they reach a certain level of technological advancement. That's why Oxford philosopher Nick Bostrom states that no news is good news. The discovery of even simple life on Mars would be bad news, because it would rule out a number of potential great filters that we've already overcome. If we were to find fossilized, complex life on Mars, Bostrom says, it would be the worst news ever printed on the cover of a newspaper. There is also a second set of explanations for the Fermi paradox, that Type 2 and Type 3 civilizations do exist, and there are logical reasons why they are silent. The logic here is simple. There is nothing particularly unusual or rare about our galaxy, our solar system, our planet, or our intelligence level, at least not until proven otherwise. Our search for extraterrestrial signals currently covers a region of space within 100 light-years, which is only 0.5% of the Milky Way. Given this, is it really so remarkable that we haven't heard anything, and that no one can hear us? Consider this. America was colonized by Europeans long before the small Inuit tribes in the far north of Canada even knew of it. Perhaps interstellar settlements of more advanced species have their own systems of urbanization, where neighboring solar systems are colonized to some extent and maintain communication with each other. In such a case, traveling to our distant corner of the galaxy might be neither practical nor purposeful. Moreover, the very idea of physical colonization might seem pointless to more advanced civilizations. For instance, Type 2 civilizations might have crafted the perfect environment to cater to all their needs, with no interest in exploring a cold, empty universe. Even more advanced civilizations might view the physical world as an exceedingly primitive place. They may have long since transcended their biological limitations and uploaded their consciousness to a virtual reality, granting them eternal life. To them, the physical world of biology, mortality, and needs may seem as irrelevant as the life of primitive oceanic creatures in a cold, dark sea does to us. Virtual realities could offer an ideal world where everything is at one's fingertips. In such a reality, one could be anyone and do anything, with no restrictions. Why would they leave that for the dangers of space travel? Carl Sagan offers another thought. While there may be plenty of activity and noise around us, our technology is too primitive to detect it. It's like walking into a modern office building, turning on your walkie-talkie and hearing nothing, leading you to believe that no one is in the building. Furthermore, Sagan suggests that our brains may function much faster or slower than those of another form of intelligence. For example, it might take aliens 12 years to send a simple hello. When we finally hear that message, it may sound like white noise. Alternatively, they might send extremely fast signals designed for similarly advanced civilizations, leaving us with our primitive minds unnoticed. To them, we might be of no interest. Stephen Hawking famously stated, "If aliens visit us, the result will be similar to what happened when Columbus landed to the Americas, which did not turn out well for the Native Americans. We desperately want to know if we are alone in the Milky Way. We long to shout out, to announce ourselves to anyone who might be listening. But what if doing so is the last mistake we ever make? Imagine a hunter waking up in his hiding place. Before rising, he listens cautiously for any suspicious sounds from the dense thickets. Another night has passed without incident. The forest is dark and thick with fog. The hunter wants to call out to others to relieve his loneliness, but at the last moment, he stops himself. What if they are just like him? All living creatures strive to survive, secure resources, and reproduce. The primary obstacle is other creatures with the same goals. Competition between species favors those with advantageous traits. Our ancestors were resourceful, competitive, expansionist, and driven by a desire for resources. These traits enabled them to win the intellectual race. Today, most other species are so defenseless against us that we unintentionally wipe out dozens of them every day simply as a byproduct of our lifestyle. But humans are more than just individuals. We create cultures that compete with each other. A competitive, dynamic society tends to spread faster and farther. If we look at our history, it is clear. We are not only dangerous to others, but also to ourselves. Human nature has driven us to occupy every corner of this planet, and now we look to the stars. We seek to expand our influence and access more and more resources. And it is at this point that we may encounter others who are doing the same. It is likely that competition for survival exists on other planets as well. Therefore, it is logical to assume that an alien civilization capable of dominating its planet would share certain traits with us. Imagine that you are a hunter, sneaking through a dark forest. You are alone, but you know that somewhere there may be others like you. You cannot know their intentions, whether they are peaceful or aggressive. You realize that just as you might kill for your own survival, others could do the same. If you encounter another hunter, the one who shoots first may survive. But that doesn't mean conflict is inevitable. So far, the progress of modern civilization seems to have made us more peaceful rather than more violent. This could also apply to other civilizations. Progress might lead to reduced conflict. However, alien civilizations could vary greatly, with some being peaceful and others being more hostile. The challenge we face is that when we encounter extraterrestrials, we will have no way of truly understanding their intentions. Similarly, they may not have any clear sense of our motives either. Additionally, if we discover another civilization, they will likely discover us as well. The vast distances between us will result in delayed communications, leaving both sides in a state of uncertainty. We could find ourselves wondering whether it might be safer to strike first. There are two major issues here: technological advancements and the advantage of the first strike. While we don't know the ultimate limits of technology, we do know that technological progress can drastically alter the outcome of a conflict. A few hundred or 1,000 years of advancement could turn an uncertain battle into a one-sided defeat. For instance, Caesar's legions would stand no chance against World War I artillery, and even modern drones and guided missiles would easily overpower World War I forces. The technological disparities between civilizations could be staggering. Even if we were to make contact with a civilization at our level, by the time they respond, we might already fall far behind them in terms of technology. The issue becomes even more critical when considering the vast differences involved in interstellar conflict. If an enemy is light years away, it may take so long to send an invasion fleet that it becomes outdated by the time it arrives. The only way to ensure access is to strike quickly and with overwhelming force, leaving the target with no chance to retaliate or escape. Assuming most civilizations live on planets, they are inherently vulnerable. A single large object dropped on a planet could easily render it uninhabitable. For example, a meteor the size of a person, traveling at 95% the speed of light, would release energy equivalent to all the nuclear bombs on Earth. A few dozen meteorites aimed at a civilization would almost certainly result in its destruction. This might not be as far-fetched as it seems. A civilization even slightly more advanced than ours on the Kardashev scale would have the ability to launch multiple devastating strikes on any planet with life. What makes this kind of weapon so terrifying is the overwhelming advantage of the first strike. It could be so fast that defending against it would be nearly impossible. The first to strike often has the upper hand. This dynamic makes every civilization a potential existential threat to every other. If all civilizations are threats to each other, perhaps there are only two types of civilizations in the universe: the silent and the extinct. So what should we do? Should we be concerned? The radio signals we've been sending out for the last century have only traveled a relatively short distance and are now just noise in space. With our current technology, unless we are deliberately trying to make contact, it's unlikely anyone would notice us. However, scientists are developing new methods to search for biosignatures, chemicals like oxygen and methane, that might indicate the presence of life on distant planets. If extraterrestrial civilizations have powerful telescopes, they may have detected the oxygen in Earth's atmosphere long ago. Perhaps we're approaching this problem incorrectly. Maybe our primitive minds, shaped by a history of fierce competition for survival, are naturally inclined to suspect predatory aliens lurking nearby. Maybe our perspective on the universe signals that we have not yet evolved as a species to fully understand the implications of contact. This could be why some scientists believe there might be a peaceful network of civilizations out there, waiting for us to mature before making contact. Imagine there exists a single super-intelligent civilization, which we'll call Alpha. This civilization has not only surpassed us in technology, but has reached a level of advancement that we can't even begin to grasp. Alpha was the first to emerge in the galaxy, and after billions of years of existence, has developed technologies that allow it to control vast regions of space. It can observe the birth and evolution of life on distant planets, while remaining completely undetectable. For Alpha, most life forms are insignificant and unworthy of attention or concern. Simple organisms, plants, and basic animals come and go with no effect on Alpha's plans. However, occasionally a species arises that begins to exhibit signs of intelligence. Alpha may pay special attention to such species, studying their cultural and scientific advancements. But there is a limit, a threshold that no civilization can cross without Alpha intervening. This threshold might be reached when a species masters interstellar travel or begins emitting powerful signals into space. When that moment comes, Alpha may act. To Alpha, this is like an immune response to a potential threat. The methods Alpha uses to eliminate these rising civilizations are likely complex and undetectable by us. It could be something as subtle as altering the fundamental constants of nature in a specific region of space or triggering the detonation of a nearby star. As for Alpha-level civilization, it may be as simple as for you to click the likes below the video and subscribe to the channel. But why would Alpha do this? Perhaps it is a product of past experience. Maybe Alpha once encountered another advanced civilization, and the result was a catastrophic conflict. From an evolutionary standpoint, this makes sense. A civilization that is obsessively focused on its own survival and security could reach a point of advancement where such precautions become necessary. The survival of Alpha depends on preventing threats, and if it must, it will eliminate them without hesitation. In this context, our civilization might be a tiny, carefully observed entity in a vast protected ecosystem, like an animal in a national zoo with the rule, look, but do not touch. This hypothesis was proposed by American astronomer John Ball in 1973. According to Ball, we don't detect other civilizations because if a far more intelligent species wants to observe us in secret, they're fully capable of doing so. Perhaps there are universal protocols, similar to the Prime Directive from Star Trek, that prevent super-intelligent civilizations from making open contact with less evolved species like ours. Michio Kaku presents a relevant analogy. Imagine we have an anthill in the middle of a forest, and right next to the anthill, a 10-lane highway is being built. The question is, will the ants be able to comprehend what a 10-lane highway is? Will the ants understand the technology or the intentions of the creatures building the highway beside them? It is possible that the issue isn't the weakness of our technology, but rather our inability to understand what the super-intelligent beings are or what they're trying to accomplish. Their actions may be so far beyond our comprehension that even if they wish to enlighten us, it would be as futile as trying to teach ants how to use ChatGPT. To illustrate, let's consider Christopher Columbus. When Columbus first set foot on American soil, did he stop to socialize with the ants in an anthill? Did he go out of his way to help them? Was he hostile to them? Or did he simply ignore them as irrelevant to his mission? Most likely, the ants didn't even register on his radar, as they were utterly unimportant to his goals. This brings us to a philosophical thought experiment posed by Thomas Nagel, who asked, "What is it like to be a bat?" Nagel's point was that there is an explanatory gap between what science can objectively describe and how consciousness subjectively experiences life. Nagel emphasized that scientific explanations alone cannot give us the experience of possessing another consciousness. We humans are confined to our own internal universe, shaped by our brains, bodies, and environments. By pushing the boundaries of our own consciousness and examining the remarkable abilities of other living creatures, we can begin to imagine alternative forms of consciousness. It is crucial to recognize that our way of perceiving the world and ourselves is not the only possibility. For instance, we may never fully comprehend what it's like to be an octopus. An octopus possesses a distributed nervous system. Approximately 2/3 of its neurons are located in its tentacles, meaning each tentacle contains its own cluster of nerve cells. As a result, the tentacles can operate independently. They can think for themselves, search for food, and sense objects autonomously from the central brain. Compared to human experience, this is similar to an alien form of consciousness. Speaking of actual extraterrestrials, if they exist, their consciousness might be even more astonishing. The unique conditions on distant planets could have led to the development of entirely different senses. These beings might perceive the world through gravity, detect the chemistry of an atmosphere, sense electromagnetic fields, or even use radiation as an information source. Their perception could function like an incredibly powerful sense of smell, but manifesting as visual sensations. For example, aliens might see molecules and chemical compounds, distinguishing not only objects but also their compositions. They could have bodies and forms unimaginable to us, perhaps even gaseous or silicone-based, better suited to their habitats. Expanding on speculations further, we can envision collective intelligence, where consciousness is distributed among many individuals without a single self. We might be entirely mistaken in our understanding of reality. There are countless ways we could be profoundly wrong about everything we know. It might even turn out that life can exist in other dimensions, based on plasma or dark matter. The universe might appear one way, but actually be something entirely different. A hologram, for example. There's even a possibility that we are all part of some researcher's computer simulation from another world, and other life forms simply haven't been programmed yet. In 1871, Charles Darwin, in a letter to his friend Joseph Hooker, speculated about the origin of life on Earth in a warm little pond with all sorts of ammonia and phosphoric salts. At that time, there was a heated debate about the possibility of the spontaneous origin of life. Louis Pasteur, a chemist, had demonstrated that life does not spontaneously arise in a sealed flask. However, other scientists disputed his findings, arguing that it would take much longer for chemical substances to evolve into life. If life did indeed originate this way, we must assume that a combination of molecules somehow formed in a complex chemical broth, and that all living things are nothing more than extremely intricate chemical systems. This idea remains as unpalatable to many people today as it was 150 years ago. Opponents of this theory argue that life is too complex and intricately organized to have arisen by chance. Perhaps this aversion stems from the fact that our understanding of the world at the molecular level is deeply tied to notions of randomness and probability. In school, we are taught that matter is composed of particles moving within volumes of gas, liquid, or solid. However, to describe the molecular world as one of randomness misrepresents the fundamentals of chemistry. When Charles Darwin was seeking evidence of evolution by natural selection, the Austrian scientist Ludwig Boltzmann was developing a unified theory to describe the general properties of substances based on the idea of atoms as fundamental building blocks. Many of his contemporaries considered the very notion of atoms to be insane. Nevertheless, Boltzmann incorporated his ideas into thermodynamics. He explained phenomena such as pressure, temperature, and the volume of a gas through the movement and collisions of its constituent atoms or molecules. Boltzmann's discoveries had a significant impact on the understanding of chemical reactions. His student, the chemist Svante Arrhenius, established the dependence of the rate of a chemical reaction on temperature. This relationship shows that a molecule must possess a threshold energy to undergo a reaction. As temperature increases, more molecules gain enough energy to overcome the energy barrier and participate in the reaction. You might be wondering what all this has to do with alien life. The fact is, the ideas of Boltzmann and Arrhenius identified a temperature range in which chemical transformations that could lead to life might occur, a kind of chemical Goldilocks zone. At too low a temperature, reactions are very slow or impossible. At too high a temperature, selectivity is lost and all compounds break down. Temperature is not the only factor that determines chemical reactions. It is a mistake to think of chemistry as the realm of randomness, and here's why. The molecular world is not composed of shapeless particles. Atoms combine into molecules according to strict rules that depend on their structures and electron shells. For example, the bond between carbon and hydrogen is very stable and only breaks at temperatures of 300 to 400 degrees Celsius. This bond is symmetrical. The electron pairs are evenly distributed between the atoms. The bond between carbon and oxygen is also strong, but the electrons are shifted toward the oxygen, creating a polarized bond. Carbon gains a slight positive charge, and oxygen gains a negative charge. Molecules with separated charges easily bond together due to electrostatic attraction. Thus, chemistry follows regularities rather than randomness. Complex structures, and even life, arise from subtle differences in the positions and interactions of electrons. It is the diversity of atoms that creates the opportunity for the origin of life. Without this diversity, the chance for the emergence of life simply would not exist. In the real world, unlike controlled laboratory conditions, numerous chemical reactions occur simultaneously at different rates, leading to the formation of various substances. In the 1950s, biochemist Boris Belousov discovered an unusual phenomenon. Some simple chemical compounds, when mixed, cyclically changed color. This contradicted the prevailing notion that chemical reactions proceed only in one direction, and his colleagues considered Belousov's findings implausible. In fact, Belousov had discovered a chemical oscillating reaction where molecules are formed and consumed according to certain rules, creating feedback loops. This is analogous to cyclical changes in animal populations in nature. Around the same time, mathematician Alan Turing suggested that complex structures could emerge in such systems if they were not distributed. Over the next 70 years, research has shown that such systems can indeed spontaneously produce patterns resembling animal coloration. These are purely chemical processes unrelated to biology. For example, the Belousov-Zhabotinsky reaction involves chemicals interacting in a way that creates periodic changes in the concentration of reaction products. These patterns resemble the spotted coloration of leopards, cheetahs, or salamanders. In these animals, spots are formed by the interaction of pigments. Similarly, reactions leading to the formation of Turing patterns produce stripes and spots, which are also common in nature. A similar phenomenon likely occurs on billions of potentially habitable planets. It only requires a constant supply of energy from a nearby star to keep the molecules active. Defining life is very difficult. As Lynn Margulis said, there are many definitions of life, and none of them are satisfactory. Some phenomena, such as forest fires or growing crystals, fulfill criteria for living things. They self-organize, grow, use energy, and distribute matter. However, we know they are non-living. With viruses, the situation is the opposite. They appear purposeful, but have no metabolism of their own, and are often excluded from definitions of life. The lack of clear definition of life makes it difficult to study its origin. For example, many definitions do not consider the environment as integral to life. Take NASA's definition. Life is a self-sustaining chemical system capable of Darwinian evolution. All living organisms are inextricably linked to their environment. Even humans cannot exist without constant respiration. Some species can temporarily suspend life activity, but cannot do so indefinitely. The key concept here is vitality. Life exists through activity. Therefore, when searching for the source of life, it is more reasonable to look at the source of vitality, that is, the active use of the environment for gradual growth. All living things utilize the environment for self-replication. This approach allows both viruses and cells to be included in the concept of living things. Viruses exploit the rich environment inside host cells, using their energy and machinery for replication. They minimize their own resources by relying on the environment. In contrast, plants depend less on their immediate environment, needing only light, water, and carbon dioxide. They have a complex biochemistry that allows them to synthesize everything they need. There is a simple rule. The less dependent an organism is on its environment, the greater its biochemical complexity. But dependence always remains. Without key environmental resources, plants, fungi, and humans will die. Despite the diversity of life, the basic pattern of cellular activity is the same for all terrestrial organisms. They obtain energy from outside and use it to grow and reproduce. A key mechanism is the accumulation of electrical charge on either side of thin cell membranes. At the molecular level, the strength of this electric field is comparable to that of lightning. Alongside DNA, the electric charge across cell membranes is a fundamental feature of terrestrial life. Its stable existence suggests specific conditions were necessary for the origin of life on Earth, conditions that may also exist on other planets. In the 1960s, the eccentric biochemist Peter Mitchell proposed the revolutionary idea that cells are powered by electrical energy. Mitchell's hypothesis sparked intense debate, leading to a conflict famously known as the Oxford Wars. Ultimately, the controversy concluded with Mitchell being awarded the Nobel Prize in Chemistry in 1978. His theory was recognized as groundbreaking, with its importance compared to the ideas of the greatest scientists of the 20th century, Einstein, Heisenberg, and Schrödinger. It has been called the most unexpected concept in biology since Darwin's theory of evolution. Mitchell became interested in how bacteria maintain their internal environment. He discovered that they actively pump molecules across their membranes, a process that is energy-dependent and selective. Mitchell's genius allowed him to apply this principle to cellular respiration. He realized that energy is released when substances are transported back across the membrane. In cellular respiration, protons are pumped across membranes. This creates a difference in concentration and electrical potential. The tendency of protons to return across the membrane generates the proton motive force, the main source of energy for living organisms. Every second, an enormous number of protons, about 10 billion trillion, pass through mitochondrial membranes. This mechanism operates continuously in all living organisms, from humans to animals. Here's how it works. When we breathe in oxygen, we use it to oxidize the food we have consumed, releasing energy. This energy helps move protons across cell membranes. Simultaneously, electrons from the food are transferred through a chain of transporters in the mitochondrial membrane until they combine with oxygen. This flow of electrons powers proton transport. Most bacteria can generate a proton motive force without oxygen or organic food molecules, using other gases and minerals. Genetic studies indicate that the mechanism for creating a proton motive force already existed in the last universal common ancestor of all living organisms. This suggests that electrical energy may have been the primary source of energy for life, not only on Earth, but throughout the universe. The proton motive force is one of the strong arguments used by scientists who believe that life exists only on Earth. Their view is based on the studies showing the extremely low probability of life arising spontaneously. For example, biologist Eugene Koonin proposed a model in which the probability of the random appearance of the first replicating molecule is extremely low. His calculations yield a probability of 10 to the negative 1,000th power, which is virtually indistinguishable from zero. According to his theory, there was no need for a gradual evolution of the RNA world. Instead, a minimally complex system capable of biological evolution emerged suddenly. Koonin called this the biological Big Bang, or threshold stage. The development of life on Earth went through other improbable stages. The first was oxygenic photosynthesis, which took about 1 billion years to create an oxygen-rich atmosphere. This led to the mass extinction of organisms that were not adapted to oxygen. However, this event paved the way for the development of more complex life forms, eventually leading to us. The next stage was the emergence of eukaryotes, cells with a nucleus, which occurred through symbiosis and took another 500 million years. Then, multicellularity developed, which took another billion years. It appears that complex life on Earth emerged just in time, before changes in the sun's luminosity would have made the planet less hospitable. If the process had been delayed by another billion years, Earth might have undergone a runaway greenhouse effect, becoming more like Venus. Some might argue that red dwarfs are excellent candidates for hosting life. They can live for trillions of years, and there are 10 times as many of them as stars like the Sun. Even our nearest stellar neighbor, Proxima Centauri, has a rocky planet within its habitable zone. While this is true, red dwarfs also present significant challenges. Early in their lifespans, they undergo periods of intense stellar outbursts lasting tens of millions of years. These flares can vaporize water and destroy any emerging life. After this period, the star's luminosity drops dramatically, potentially making orbiting planets too cold. Another issue is tidal locking. Planets around red dwarfs often become tidally locked, with one side always facing the star. This creates extreme conditions, perpetual daylight and heat on one side, and eternal night and cold on the other. While a thick atmosphere could mitigate these conditions, another problem arises: retaining that atmosphere. The magnetic field that protects a planet's atmosphere from stellar winds depends on its rotation rate. Tidally locked planets have slow rotations, resulting in weak magnetic fields. This can lead to atmospheric loss, as happened with Mars. When lecturing on cosmology, I often ask for a show of hands from listeners who believe there is intelligent life somewhere in the universe. And in any audience, from kindergartners to college students, these are invariably the majority. When I ask why, the most common answer I hear is that the cosmos is huge, and somewhere, statistically speaking, there must be life. But is that argument valid? I think not. Here's what statistics tell us. It all comes down to one number: the average distance between civilizations. Imagine that intelligent species are scattered randomly throughout the universe. The key parameter is the average distance between a typical civilization and its nearest neighbor. If the average distance exceeds 20 billion light-years, then we are effectively alone in the observable universe, because at that distance, the statistical probability of encountering another civilization drops to 0. Let's consider this further. The observable universe is the part of the cosmos from which light has had time to reach us in 13.8 billion years. Due to the expansion of the universe, its radius is now about 46 billion light-years. Taking further expansion into account, Tegmark's calculations result in a figure of 200 billion light-years. If the nearest civilization is farther than this distance, we will never be able to contact or detect it because light from it has not yet reached us and may never reach us due to the accelerated expansion of the universe. Frank Drake, an astronomer and astrophysicist, proposed a famous question that estimates the number of active, communicative extraterrestrial civilizations in the Milky Way galaxy. Drake identified several key parameters, including the fraction of stars with planetary systems, the number of planets that could potentially support life, the fraction of planets where life actually appears, and the development of intelligent life. Thanks to the recent discoveries of exoplanets, we now know that there are many potentially habitable planets, billions in our galaxy alone. However, the likelihood of life developing on them and the emergence of intelligence remains highly uncertain. Suppose the first living cell appeared. It requires a ribosome, a complex molecular machine that reads genetic code and synthesizes proteins. But here's the paradox. To create a ribosome, you need another ribosome. It's akin to the chicken and egg question of which came first. Scientists still can't fully explain how the very first ribosome originated. Consider the development of intelligence. Dinosaurs dominated the Earth for over 100 million years, which is about 1,000 times longer than humans have existed. Yet during that vast span, they never developed advanced intelligence or invented tools like telescopes or computers. It appears that evolution was in no hurry to make them smarter. Why is that? We don't know. Given this uncertainty, the probability of intelligent life arising on a planet could range from 1 in 1,000 to 1 in a quadrillion, with roughly equal likelihood. Our astronomical observations have so far found almost no evidence of intelligent life. This suggests that the fraction of planets hosting intelligent beings is extremely small. There is probably no highly evolved intelligent life within a radius of 10 to the 21st meters, which encompasses our galaxy and its immediate vicinity. This assumption by Tegmark is based on several premises: that interstellar colonization is possible, that billions of potentially habitable planets exist in the Milky Way, and that the probability of life colonizing the cosmos is not negligible. Colonization could be achieved through various means, such as self-replicating probes. While some scientists propose that advanced species may not be interested in colonization, it would only take one expansionist civilization to spread throughout the entire galaxy. Considering these factors, the nearest civilization is probably between 10 to the 21st power and 10 to the 100th power meters away from us. However, since the radius of the observable universe is about 10 to the 26th power meters, we can narrow down all the possible distances. Specifically, it must be between 10 to the 22nd power and 10 to the 26th power meters. This leads to the conclusion that we are most likely alone in the observable universe. To reiterate, out of the entire range of distances from 10 to the 21st power to 10 to the 100th power meters, the possibility of not being alone in the observable universe only exists within the narrow window between 10 to the 22nd power and 10 to the 26th power meters. Is it really so probable that we fall precisely within this narrow range? There is another explanation for why we seem to be alone. We are simply early. This hypothesis is known as the grabby aliens theory, proposed by Robin Hanson, the same researcher who introduced the concept of the Great Filter in 1996. A couple of years ago, Hanson and his colleagues published a paper detailing this new model. This model attempts to explain why we haven't found aliens despite the vast number of stars and galaxies. According to this theory, some civilizations become grabby. They actively spread throughout space, leave visible traces, and exist for a long time. Hanson builds upon Brandon Carter's model of hard steps, which posits that evolution goes through a series of unlikely transitions. This model explains why we appeared so early in the history of the universe. We are simply the fortunate ones who progressed through all the steps faster than others. The concept is analogous to cancer development, where a cell must undergo several mutations before becoming malignant, usually 6 or 7 mutations, but sometimes as few as 2. Hanson estimated that Earth may have gone through 4 to 12 hard steps. This model can be applied universally, providing a formula to estimate the probability of advanced life arising at a particular time and place. Interestingly, the more such difficult transitions are required, the later advanced life should emerge. However, humanity seems to have appeared relatively early. In Hanson's calculations, represented graphically, the horizontal axis shows the maximum lifespan of stars with habitable planets, while the vertical axis indicates the number of difficult transitions. The color scheme on the graph illustrates how early we are. Cool colors indicate we are not that early, whereas warm colors suggest we are very early. Interestingly, in many combinations of parameters, humans rank among the top 1% of all evolved life forms in the universe. For example, suppose the maximum lifespan of a planet is 10 trillion years, and the number of difficult evolutionary transitions is 10. The probability of our existence then turns out to be 1 in 10 quintillion, which seems suspiciously low. So what if we use more conservative estimates? 6 difficult transitions and a maximum planetary lifespan of 10 billion years. Humans still fall into the top 10% of all evolved life forms. The early emergence of humanity raises an intriguing question for scientists. Why did it happen? When the facts don't fit the model, that is, they have an extremely low possibility, it may be worthwhile to revisit our assumptions and seek more plausible explanations. According to Robin Hanson, it's all about grabby aliens. These are civilizations that rapidly occupy all habitable planets, essentially aspiring to become a Kardashev Type 2 civilization. According to the model, civilizations like ours can only arise in the early stages of the universe, where there are still free planets. Right now, we appear to be a typical non-grabby civilization. as we are completely invisible on the galactic scale. Hansen believes that in time we may become grabby. Consider how Earth's cultures and organizations exhibit expansionist tendencies. They occupy new niches and territories at the first opportunity because such behavior is evolutionarily successful. Imagine two species that consume the same resources. One species is content with its territory, while the other is constantly expanding. Over time, the expanding species will supplant the first as its population grows with each generation. The principle may be universal for extraterrestrial civilizations as well. Grabby species expand and occupy all habitable space, preventing new species from emerging. In doing so, they leave noticeable footprints, for example by harnessing the energy of stars with Dyson spheres. Hansen suggests that interstellar travel is possible, but not necessarily via crewed ships. More likely it is the use of self-replicating probes, known as von Neumann probes. These devices could colonize new planets and seed life. Various technologies, such as solar sails, could be employed to propel such probes. Scientists estimate that colonizing the Milky Way could take between 5 and 900 million years, which is relatively short compared to the age of the universe. Let's understand how this is calculated. The hypothesis is based on a simple mathematical model with 3 parameters: the rate of appearance of grabby civilizations, their rate of expansion, and the number of difficult evolutionary transitions. By substituting values, we can estimate the likelihood of the emergence of grabby species. Hansen notes that even if the probability of grabby aliens appearing is extremely low, their impact on the universe could be enormous. So, why aren't we seeing them? This model predicts that we shouldn't see them because if grabby aliens were visible from Earth, they would already be here. According to the calculations, the faster grabby species disperse, the less likely we are to observe them. Here's why. We have 2 main factors: the rate at which the aliens are expanding and the number of difficult transitions required. A graph illustrates how these 2 factors affect the likelihood that we won't see grabby aliens. The blue areas on the graph indicate that if aliens exist, we are likely to see them. The yellow areas suggest the opposite, that we are unlikely to see them. Interestingly, the speed of alien expansion affects this probability much more than the number of difficult steps. For example, if their ships travel at 70% the speed of light, we are 100 times more likely not to see them than if they travel at 10% the speed of light. The model suggests that if aliens are traveling slower than 1/3 the speed of light, we should be able to see them. If we can't see them, that implies they are traveling faster. This explains why we haven't detected aliens. They're moving so quickly that their light hasn't reached us yet. The model makes other interesting predictions. Simulations show that grabby civilizations appear during a certain period, 5 to 10 billion years after the origin of the universe. Most of them emerge by the 20 billion year mark. Surprisingly, according to the model, our civilization could either be one of the first or one of the last grabby civilizations. The probability of being among the first 18% is the same as being in the last 28%. I believe you've noticed that Hansen's entire hypothesis rests on 2 main assumptions. The first is that we are destined to observe grabby civilizations because they inevitably leave detectable traces. However, this is merely speculative. It's possible that we don't yet know what signs to look for, and future technologies could aid us in this search. If that's the case, then we could soon detect grabby aliens. Their traces might cover an area of the sky larger than the full moon. The second assumption is that highly intelligent species will find ways to travel at very high speeds. Currently, we don't know if that's technically possible. However, assuming it is, scientists have already contemplated some aspects of it. In 2014, physicist Jay Olson conducted a study exploring high-tech methods of dispersal. He proposed using 2 types of probes: seed probes and expanders. Seed probes would approach their destinations, decelerate, land on planetary surfaces, and initiate the creation of new civilizations from scratch. Expanders, on the other hand, never stop. They collect matter as they travel and use it to create copies of themselves, minus the portion used as fuel for propulsion. A fleet of self-replicating expanders would move with slight acceleration to maintain a constant speed relative to nearby galaxies. Simultaneously, the expanders would rapidly reproduce to sustain their fleet. Another method for civilization to spread across the universe is both the fastest and most dangerous. Max Tegmark refers to it as the Siren World method, drawing on Hans Moravec's idea of space spam. The essence of this approach is that advanced civilizations send radio signals into space to attract the attention of less advanced species. These signals contain information that prompts recipients to create superintelligent machines, which then take over the recipient civilization, effectively transforming it into a copy of the sender. This method allows a civilization to spread virtually at the speed of light, the speed at which these signals travel. Given this may be the only way to reach most galaxies, a superintelligent civilization might be tempted to use it. Remember the movie Contact, where humans used schematics received from aliens to build a giant, incomprehensible machine? To quote Tegmark, "Oh, I wouldn't recommend doing that." If life isn't rare after all, we may soon discover it. Astronomers are actively searching for signs of life in the universe, studying the atmospheres of Earth-like planets for indicators like oxygen and methane. There's also the search for intelligent beings through projects like Breakthrough Listen. It's important not to be too anthropocentric in our search. If we find an extraterrestrial civilization, it will likely already be intelligent. Cosmologist Martin Rees put it this way: "The history of human technological civilization is measured in centuries, and there may be only 1 or 2 centuries left before humans are overtaken or merged with inorganic intelligence, which will then persist, continuing to evolve for billions of years. It would be extremely unlikely for us to catch a different mind in that brief moment when it is still taking organic forms." Jay Olson believes it's highly unlikely that advanced civilizations would limit themselves to repopulating planets with their advanced copies. This doesn't seem like the final stage of technological development. So when imagining aliens, don't think of them as green beings with large eyes. Consider superintelligent, space-filling life forms. While I wholeheartedly support all ongoing searches for extraterrestrial life that could shed light on one of the most fascinating scientific questions, I secretly hope for their failure. I cross my fingers that the search for extraterrestrial life ends in failure. It would fit nicely into a scenario where the development of intelligent life is rare. But we humans have been unspeakably lucky, and the barrier is behind us, and we have an incredible and fantastic future ahead of us. Our lifespan is insignificant compared to the cosmic timescale, but this short century is perhaps the most significant in the history of the universe. Its future is being decided now. We have the technology both to self-destruct and to seed the cosmos with life. This situation is so unstable that I doubt our ability to stay at this fork for more than a century. If we eventually choose the road of life over death, then in the distant future, the cosmos will be abundantly populated and all life will have a beginning in the here and now. Thanks for watching. If you liked it, put likes, subscribe to our channel, leave comments, and share this video with your loved ones. It helps a lot.